Welcome to the second episode of BSc Bit-Sized Concepts. Here we take a closer look at big scientific ideas, not with heavy math, but with sharp clarity and deep insight. And today's topic is very interesting. What is Einstein Field Equation? Well, first we need to understand that what exactly is Einstein Field Equation before we go into the deep mathematics of it. So if I go by the definition, Einstein Field Equation is the foundation or the core mathematical formulation of general relativity, and it actually is a set of 10 interrelated different kind of nonlinear partial differential equations that actually describes the geometry of space-time, which is determined by the distribution of mass, energy and momentum within it. Now there are different forms of Einstein Field Equations which come across in different textbooks, websites, etc. So the standard form which is being mentioned is this one. This is basically called the standard form. Then we come across something which is called the original vacuum free form, and this was actually the original 1915 equation of Einstein, and here there is no cosmological constant. It is applied in many classical problems of GR. Then we get a geometric form of Einstein field equation, and in this video we will look in this form because it is quite easy to deal with the mathematics. Then comes what is called the trace reverse form of Einstein field equation. This is useful in linearized gravity or weak field approximation, and this form actually avoids using Einstein tensor and directly expresses as R mu nu. Then we get a compact notation using Einstein's summation, and this is a shorthand in common and is used mostly in the equations of theoretical physics. So all this 1, 2, 3, 4, 5, and maybe there are other forms of Einstein field equations. What it tells is simply this: if I take the geometric form, the left hand side of the equation actually denotes the measurement of the curvature of space-time. That means how space-time is curved, and the right hand side denotes basically the matter content. That means what is actually responsible for causing the curvature, obviously the matter. So as John A. Wheeler has put up in his famous quotation, space-time tells matter how to move and matter tells space-time how to curve. This is all in all. In short, we can talk of the Einstein field equation, different geometric and standard and vacuum solutions actually denoting one simple thing. The left hand side is measuring the curvature, the right hand side is measuring what causes the curvature, that is the matter content. Now there is a very interesting history, or I would say interesting chronology, in which Einstein actually discovered Einstein field equations. So we come to what is called the birth of Einstein field equation. Now within this 1907 to 1915, I would say 1905, when Einstein proposed special theory of relativity, he started actually working from inertial to non-inertial frame of reference. And during that time when he was working, he actually told that he has arrived at the happiest thought of my life. So that is quoted as the annus mirabilis, or the golden years, the happiest thought of his life. Now what was the happiest thought? Now if you look at the picture down below on the right hand side, this actually beautifully captures Einstein's insight. So you are in a stationary box under gravity and you feel the same as being in an accelerating box in space. So you feel the pressure under your feet when you're standing, and the same pressure you feel when you're accelerating upwards. Similarly, a free-falling box in a gravitational field is actually indistinguishable from a box moving at a constant velocity in the absence of gravity. Hence, actually what Einstein wrote is this: the gravitational field has only a relative existence. That means for an observer freely falling from the roof of a house, God forbid that you do not fall, at least in his immediate surrounding there exists no gravitational field. This is a remarkable insight. History tells that it is considered to be the happiest thought of his life, and the entire science, the way we perceive space and time, forever changed for that. Now it was not only Einstein, actually it started with his friend, a Swiss mathematician who was a master of differential geometry by the name of Marcel Grossmann, and he actually introduced the concept of tensor calculus to Einstein, the entire Riemannian geometry and whatever. And this is what you can see is written in German. The translation says, outline of a generalist theory of relativity and a theory of gravitation. In German it is called Entwurf, or you can call it as a draft. So in Einstein, this Entwurf document actually laid the seed of developing what is called a covariant theory of gravity. And with Marcel Grossman, Einstein worked closely with the differential geometry and other complicated mathematics to arrive at 1915. So now there is a kind of a debate. We are not going in that who actually published the field equations first. Some people say David Hilbert, some people say Albert Einstein, but whatever, science got one of its best kind of a theory. So November 1915, Einstein presented the form in the form of Einstein Field Equations. Shortly after, David Hilbert had submitted a similar kind of a formulation on the Einstein Field Equations. This is the famous paper written in German, which is actually the paper which cited and published what is called Einstein Field Equation. If you're following me on thread, then I have given a complete English translation, and the date is very important, November 25th, 1915. So it took almost 1905 to 1915, 10 years for Einstein to develop, and is submitted to the Prussian Academy of Sciences, and it marked what is called the birth of general theory of relativity. Now, most importantly, once we understand the birth and the genesis of a field equation, we come to the next part, that what it actually tells. Now, it tells one very simple thing, that gravity is not a force. So considering the Newtonian gravity, where there are point masses, and you can see in the animation that the apple is falling down, the famous Isaac Newton's revelation of gravity as a force. Gravity in Newtonian physics is actually described as a force that acts instantaneously across different distances. Now you can see this is this actually force actually creates those the Earth and the other planets orbiting around a heavy mass, the apple falling from the tree and everything. But here, as you can see, that gravity is not a force. So the animation actually shows that the marble, there is no force that is moving the marble. It is just following what is called the curved surface. So no more there is action at a distance. Changes in gravity propagate with the speed of light. And here you can see gravity is not a force and transmitted across space, and that actually made a famous discovery which we lately saw as called the gravitational waves. So the curvature of space-time, a shift from Newtonian force, a fictitious force which is keeping the planet's orbit and other things, are now called as a space-time curvature. And this is why this actually explains what is called the gravitational waves, or what we call the ripples in space-time. It also depicts a wonderful kind of a concept which is called this. As you can see here, the light actually takes a curved path. Actually, the light takes a straight path, but it is basically the curvature of the space-time that the light appears to go in a deflected path, and it is not a straight line. So here in Newtonian physics, if I go, light has no mass. Gravity should not affect it. So Newtonian gravity actually cannot explain why light could bend near a star. So in general relativity, mass and energy are curved space-time. So light always bend in from a straight line and in context of the space-time. So the star behind the sun appeared to be little bit shifted. It is also called gravitational lensing, which is recently got a wonderful picture of JWST. So here you can see a heavy mass, the space-time is curved, and the light is bending. Now this was actually formulated in 1915, but it took almost, I would say, 5 years or 4 years when Arthur Eddington, through his famous, 10th of November, that was on 1915, 1990. So 4 years when actually Arthur Eddington did his experiments, and through this experiment he found the deflection of the light. So this was a famous experiment when the solar eclipse happened, and it happened actually on the 29th of May 1919, and the results got published in New York Times on 10th of November 1919. As you can see here, the delta theta is basically what is actually causing the shift. So stars behind the sun, which appeared slightly shifted, actually matched exactly with Einstein's prediction. This was a triumph for Einstein's theoretical understanding of general general relativity in something which we can actually see, and this was done by Arthur Eddington. Well, we next come to the core of the understanding of Einstein's field equation, what is the meaning of that equation. Now, in order to know the meaning of the equation, what we now need to do is that first we look into the constant values of Einstein field equation. As I told, I will be covering this form of the equation so that you can understand. Now, the first thing, if you go through the equation, you will see that there are already certain things that you know. The first thing is that you already know what is lambda. This is the capital lambda, or cosmological constant. Then there are other constant which is called c raised to the power 4. This is the speed of light. Then we call 8 pi. This is also a constant, and g, which is called the good old gravitational constant, Newton's gravitational constant. Now, all these constants are pretty important because actually it gives or sets the limit or the strength of interaction between matter, energy and curvature. What do I mean by that? So if you get the good old G, gravitational constant, if you get a greater value, that means gravity is stronger. On the other hand, if you see c raised to the power 4 for the fourth dimension of space-time, it ensures both sides of the equation must have the same units. Next, we come to this important factor, 8 pi g upon c4. This is the coupling strength of the matter, energy and curvature. That means it tells how much space-time bends per energy moment. So you can think of it as a volume knob. It sets how strongly input turns into output. It scales the response and it does not enforce anything maximum. So this actually sets the limit. The constants that you already know, 1/2 is coming out of derivation, so that is also a constant. Now we explore the components of the Einstein field equation one by one. For that, first we explore what is called this R. This is called what is called a Ricci tensor or a Ricci curvature tensor, and it tells how a volume moves in a curved space. Now, if you imagine this to be a sphere, and if you see that these lines or the geodesics technically are converging at a point, this means it has got what? A positive curvature. So if I take a volume and start moving through this and this, you will see that it is shrinking. Similarly, if you so the shrinking actually tells that how volumes changes in curved space-time. Again, if I take two lines parallel and if I move something, it really doesn't changes, so it is flat. So the Ricci tensor is 0. Again, here you can see, as I have shown you in the animation, this thing is converging, so Ricci tensor is greater than 0, and when it is diverging, Ricci tensor is less than 0. Now note one thing importantly, that this entire field equation has got two R's. The first R has got a mu nu, the second R have not got. And what is the reason? We will come to that part very soon. So the first part, R is mu nu, it is a tensor component, it has got two indices, it tells how volume changes in curved space. Now we come to the second R. It has got no mu nu. That means there are no indices. What does that mean? It means that it is a scalar curvature. Scalar curvature means what? That it actually is a measure how the entire curvature is happening without directional preference. Now note here, very important. I have just told you that R mu nu have got a indices, and indices means that they have got directions. A scalar does not have any indices. That is why I have written that it has no directional preference. So if you consider, it actually does not tell you how a curvature behaves. That is the job of the Ricci tensor, the earlier R. So let us imagine this is to be a room. Now this room, we are trying to measure the temperature. So Ricci tensor, the first R, will measure whether the temperature is over this direction or this direction. So R mu nu actually tells how hot or cold or the temperature is behaving in different corners of the room. But if I only take the R, then it will give you the average. Well, this is a hand wavy overall kind of a thing, although there are deep mathematics in that. I'm not going right now. So the Ricci scalar gives you the average temperature of the room. That means it is a weighted average, or you can say it is a trace of how geodesics converge, diverge, or they behave accordingly. So this is basically an overview of the equation. So you see the scalar curvature P is basically a summation of the sectional curvature of the base components of the vectors EI and EJ. I'm not going to sectional curvature right at this moment, but what I'm trying to tell is that this means we sum up the directional averages and get a total average curvature, and there is no direction, and this makes things easier. So the first one gives direction, the second one does not, and it gives a directionless summary. That means overall how the curvature is in a manifold of a space-time, and this is what the Ricci scalar talks about. So the Ricci scalar actually tells how the volume of a tiny geodesic ball deviates from the volume you could expect in Euclidean space. Now we come to the second, which is called the heart of Einstein field equation G. Now this is which is known as a metric tensor. Well, let me tell you, those who are my old subscriber have a very detailed video and derivation of metric tensor. However, in the BCS bit size concepts, metric tensor is something which is a measurement. It is a measurement of the angles, the distances, the time intervals, whatever. So if I take a curvature like this, and for example, these two red are the 2 points, so I can measure the distance, the blue one, from one red dot to the second red dot. Similarly, if I take a Cartesian coordinate and if I take a spherical coordinate, I can actually tell how the metric tensor converts the coordinates of one of the actual distances into any coordinate of other distances. So metric means ruler. It is a ruler that measures the curvature of space-time in terms of angles, time intervals, etc. So the distance formula in a curved space is something like this. Don't worry if you don't understand, it is not an issue, but what it tells you is that how you find out the infinitesimal small distances between two nearby points on a manifold. So that is why we have squared the distance. I'm so sorry. We have squared the distance ds squared. So if I go a little bit mathematically to understand, in a flat space, if I take a Cartesian coordinate and I use the Pythagorean theorem, we get something like this. Now you can see this is simply an identity matrix. Now in case of a, because why? Because ds squared equals to dx squared and dy squared. Isn't it? Now if I take a curved space, something like a sphere, so there are no diagonal terms, and the coefficients are 1, so distances are uniform. But if I take a curved sphere, something like this, we get a coordinate like this. And here you need to notice that this sine square is actually the distance between the 2 points. So what it tells is that it varies with theta, obviously, because it is not a Cartesian coordinate, and it is in contrast of the coordinate and how the theta will behave. So the metric tensor here becomes something like this, not the usual metric tensor of Cartesian coordinate and identity matrix. So from here we can summarize that metric tensor is a mathematical tool that defines how distances, angles, these things are measured. As I was telling, it is a ruler. So in flat space the ruler is always the same, and in curved space things tries to take a weird turn and the ruler stretches or shrinks and it actually does the measuring thing. So we are done with R, the Ricci curvature tensor. Then we are done with second R, the Ricci scalar. We are now also done with G, the metric tensor, and we are dealing with this very interesting thing which is called the lambda, or the cosmological constant. Now what happened actually is that in 1917 Einstein introduced this lambda, thinking that the universe is static. So if the lambda is greater than 0, it will stretch out. Just for example, the Big Bang theory, it was infinitesimal, and now we are into a accelerating universe, and if it is less than 0, it would pull inward, something like this animation. It would pull inward. So that was basically the idea, because Hubble did not discover during that time. So when Hubble discovered that the expansion of the universe, it is expanding, Einstein called that to be one of his biggest blunder. So when Einstein actually completed his equation in 1915, during that time he assumed that the universe is simple, but when Hubble discovered that the universe is expanding, he considered to be a biggest blunder. Now this reminds me of a brilliant book which is called Brilliant Blunders, and here you can see all the brilliant blunders which are made by Einstein, Charles Darwin, and different other scientists. Amazing book, and here you can understand how these blunders actually turn in something which are so wonderful, and today we are dealing and understanding on those. So you can follow this book, Brilliant Blunders. It will talk about the blunders made by scientists. So here you can see that the original Einstein field equation was without lambda. But when Einstein applied this equation to the entire universe, he found that the universe must either be expanding or contracting. So there is no stable solution. And that came as a shock. Because during that time, before the Hubble's discovery, it actually contradicted with the era, with the belief of the system, of the entire society and of the entire scientific community. So what actually Einstein did is this one. He tried to, I would say, balance between the gravity which is pulling inward and the gravity which with a push which is giving outwards. So hence he used this cosmological constant. So here one thing is very noteworthy is that if you see the g mu nu component here, it scales distances and shapes in space-time. Adding lambda g mu nu is like adding a uniform contribution to curvature. So unlike the Ricci tensor r mu nu, which is sensitive to the directional curvature we have just seen, this term is something which is called isotropic. This term is isotropic and it affects all the directional gravity. And somehow today this lambda is now considered as an important factor in the research of dark energy. This is now being taken up in account, and this lambda is back and it is modeled to explain dark energy and the acceleration of the universe. So here we can summarize, cosmological constant is like a built-in energy of empty space. When Einstein introduced it, he tried to balance between the inward and the outward push of gravity, but later dropped out, and today again that blunder is back, that we are linking this to dark energy, and a lot of researches are done, and I've made certain podcasts also on dark energy. So now we are done with the left hand side, isn't it? R, the Ricci scalar, which is actually telling the overall curvature, the R mu nu, which is the Ricci tensor, then the metric tensor measuring angles and distances, the lambda, the cosmological constant to balance, and then we come to the last term, which is this T mu nu, which is called the stress energy momentum tensor. Now what is it all about? Now this guy is actually telling you that how much energy and momentum exists. That means the matter which is causing the curvature, how much energy or what are the mathematics that is involved in that. So the stress energy momentum tensor more or less looks like this. And if I take an easy depiction, it would look like this. So if I take a mass, a ball or any heavy mass which is causing the curvature, so this entire energy, density, flux, pressure, everything is responsible for causing the curvature, which is the mass. So the mass causes the curvature, and mass energy momentum tensor, this T mu nu guy, is responsible for the measurement of the mass and everything else. So from here we can actually say that is why the left hand side is the geometry and the right hand side is the physics part. Now if I take the stress energy momentum tensor as a whole, and we want to understand, what we generally do is in physics is that we model to something which is called a perfect fluid. Perfect fluid, you understand, things are static, there is no much pressure, things are not moving. So this is a perfect fluid. Now in the perfect fluid you can see that there is an energy density component, the rho, then there is a pressure in the space, and there is a zero momentum flux. So if I now map out, you can see this T00 in the stress energy momentum tensor is the rho, which is the energy density. Similarly, TII, I mean to say the indices go on and on. These are XYZ direction. So here is the energy density, here is the energy density. So we are just mapping so that we are not pulling the values so that the perfect fluid is an easy model to understand the stress energy momentum tensor. If I take these diagonal components, this is called a pressure. Here also you got a pressure. So what I'm trying to tell is that the off diagonal terms vanish because there is no shear stress or energy or flow. So the stress energy tensor momentum can be summarized as something that tells how matter and energy are distributed. The entire physics part. The left hand side is the geometry part, and it includes things like energy density, etc., which is actually responsible for the curvature of space-time. Now from here we have one component which we have not done, which is called this mu nu, And this mu nu is nothing but these are the 4 dimensions of space-time. 3 indices with the spatial dimensions x, y, z and 1 dimension of time. So you can imagine this to be a kind of a 4 dimension of time. So this mu nu has got dimensions in space-time, 4 dimensions, 4 dimensions and 4 dimensions. So all these actually add up to the dimensions of space-time. Now here is a very important question. The question is that I told you that Einstein field equation or equations, not all these dimensions of space-time are adding 4 plus 4 plus 4 plus 4. So we get some kind of a 16 components and tensors. So this brings us to the next question, that is it Einstein field equation or these are equations in a plural form. So here you need to understand that each index that we are measuring. Now mu nu, remember, is an index convention which is used in relativistic physics. But if you are going to Newtonian physics, we will be using ij. Anyway, coming back to the concept, mu nu is basically spanning over 3 spatial dimension and 1 temporal dimension, that is the time. So we can say that 4 plus 4 plus 4 plus 4, it makes up 16. So whatever you are seeing, this one, the master equation, these are actually a set of 16 partial nonlinear differential equations. But as I have shown you, these are actually 10. Now how it is? So we have a good news, and the good news is that some of the tensors are symmetric in nature. Now what do I mean actually mathematically symmetric? I won't be able to explain in the scope of the video because I have to make a different video on tensor. What it tells is that stress energy momentum tensor is symmetric. The Ricci curvature tensor is symmetric. Symmetric means what? Say for example, R01 equal to R10. Okay, R02 equal to R20. R03 equals to 30 and so on. Similarly, the metric tensor has got similar components, 01 equal to 1002. But here is a misconception. Symmetric tensors means that they do not cancel out. The components never cancel out. So the components T01, T10 or whatever it is there. The only thing is that these exist separately, but because of the symmetric nature, we don't take into account. So we don't treat them as 2 separate unknowns, but they are there in the matrix. So it doesn't cancel out, but we don't take. So we take the diagonal elements 10. We take the above diagonal elements 10, 4 at 10, 14. So then once we cancel out, we see that there are 10 independent components, and hence we are not dealing with 10 differential equations. We are dealing, 16 differential equations, not only 10 equations. So components and hence 10 equations, not 16. If you have followed my earlier videos in general relativity, I have actually shown that how this cancels out 1, 0, 0, 2, 2, 0 and it leads to 10 equations. So this is the an important part, that these are equations, not equation. And in order to know that how these equations form, so if you take any kind of a 4x4 symmetric nature of a tensor, then here you can get R00. I can just abruptly, now this might be wrong, I'm just abruptly saying you get one equation which is time equation. Now you take another random R11, what you get is the XX equation. So in this way 1, 2, 3, 4, 5, 6, these equations evolve. So even though Einstein field equation involve multiple tensors, the Einstein tensor, metric tensor, these are actually symmetric tensors. So these things are not taken into account and it remains 10. Remember, they don't cancel out, we don't consider them. Now, considering all of the equations and the space-time curvature, we have a question which is very important, central and philosophical to understand, that is Einstein field equation or equations are local in nature, or is it local in nature? What do I mean by local in nature? Now you see that when we say Einstein field equations are local, we are trying to tell that they actually relate to a curvature at one single point. It is relating to one single point. What does it mean? Say for example, a very hand-wavy kind of a mathematical equation, if I use x for g mu nu, which is the Einstein tensor, and if I use another parameter x for stress energy momentum tensor, I can draw this kind of a curved surface. isn't it? And then I put a point x. So this point x is actually telling locally how space-time curves at point x, which is this one. Clear? Now we take a box, a cube. Again, I'm taking at another x or y, whatever. So this is also at a pinpoint, how much energy and momentum is present, which is this one. So what it is telling, even if you even point a finger, you're pointing a finger, putting a pressure on the cloth and it is causing a dent. So remember, the dent that you make through a finger is right there. It is not something 10 meters or 20 meters away. So that is why it is called a local deformation. And that is because the differential geometry comes so much in use. So all the local deformation, diffeomorphism, homeomorphism, these are parts. So to cut things short, the presence of energy or mass at a point warps space-time locally. That means at a specific point. Now you might ask me now a question, is there something which is not local? Yes, there is something which is not local. For example, if I take Newton's gravitational law, the Newton's gravitational law is not local. It is non-local. Why? Because if the equation says that if there is a mass m1 and m2, it says that one object instantly feels the gravity of the object 2, and no matter how far you are. And general relativity actually corrects this by making it local, and it is mediated via the curvature. So remember that when we are talking of a local, I'm not taking quantum mechanics in this. Classical theory, local means that it will involve differential equations and derivatives at a point. So because Einstein field equations are made of partial derivatives, these are actually dealing with local interaction. There is something which is not local, which is called the Einstein-Hilbert action. Although I have made a very detailed 2-episode video on Einstein-Hilbert action. What is non-local? Now, if you take this kind of a curvature, fine, and now what I am doing is that I am taking the summation, I am doing an integral of the entire surface of the space-time curvature, this red line. So what I am doing, I am taking an integral of the entire curvature of space-time, not at a specific point. So S equals to integral of so and so, forget the other part. This is an integral over the whole space-time. So yes, it is definitely non-local in form. So here the action depends on the value of the Ricci scalar over the entire manifold, not at a definite point x, y or z. But remember, from Einstein-Hilbert action, we can actually do the variation and get what is called local Einstein field equations. So the action itself can be global, but the field equations derived are local. So when you see this type of a curvature, remember what you're pointing is a local part, this part, which I just underlined, this one, the blue arrow. So a local theory is one where what happens at a point in space-time depends only on what is happening at that point, and it is infinitesimally nearby points, whereas local is something which is a kind of a I would say an integral over the curvature of space-time. So that becomes very important, because when you are generalizing Einstein field equations over a integral which is not local, Einstein-Hilbert action comes in play. So that's all. I have just taken some of the very significant and important parts of Einstein's field equation, although it can be expanded in a lot of ways. Thank you very much for watching this bit-sized concepts which I have started new, explaining things easily and quickly. If you have liked, please do subscribe to my channel Physics for Students and click on the bell icon. And nowadays I am very active on my Facebook, LinkedIn and the thread and Instagram, where I am posting certain things which are not related typically to maths and physics, and you can follow me. You can write to my this email ID, and I will see you soon with other videos and this new series. Let me know in the comment box how this bit-sized concept is going. See you soon in the next video, but till then, may the good Lord be with you.